Bismillah ar-Rahman ar-Rahim. Welcome to chapter 6, and in this chapter we're gonna talk about the system resonance characteristics. Okay, so let us first of all have a revision about the resonance. You covered this one already in circuit course, but we can revise it very quickly. So series resonance, it is a condition in RLC circuit in which the capacitive and the inductive reactance are equal in magnitude, thereby resulting in a purely resistive impedance. For example, over here we have a circuit that consists of RLC. So the total impedance will be those connected in series. At resonance, omega L will be equal to J omega will be equal to minus 1 over J omega C. As a result, those will cancel. As a result, the total will be equal to R. And then the total impedance will be minimum. Okay, so at resonance, the total impedance will be minimum. And of course, resonance will occur when XL is equal to XC. And we know that XL is equal to omega L, XC is equal to 1 over omega C. So as a result, the resonance frequency, the equal to omega naught, will be equal to 1 over root LC. Or F naught will be equal to 1 over 2 by root LC. So this one we call series resonance circuit. Okay. Okay, what are the features of the series resonance? That the total impedance will be purely resistive at resonance. The supply voltage, of course, and the current will be in phase, because again the impedance will be mainly resistive, and the impedance will be minimum at the resonance frequency. The inductor voltage and the capacitor voltage can be much more than the source voltage. So at resonance, because of course the current will be high, then the voltage of the capacitor and the inductor can go beyond the source voltage. Okay, if we like to find the frequency response of the current, so we can find the current by dividing the voltage over the magnitude of the impedance. And then we'll find again that since at resonance the total impedance will be minimum, so the current will be maximum. So the maximum value of the current will be V over R. Okay, and if we divide the current, the peak current by 1 over root 2, that will be 0.707 I over R. V over R. So this current will intersect this curve at 2 points. So those 2 points, it will be at a certain frequency, W1 and W2, and the length of this band, we call it bandwidth. They call it bandwidth. Okay. So of course, again, the average power at that point will be I square R, or V square over R, which is the peak at the peak current. So those frequency W naught, of course, W naught is the resonance frequency, but W1, W2, we said that when the current dropped to 1 over root 2, right? So this one they call it half power frequency, because the power at that point will be half the peak value. The power over here is V square over R, and over here it will be V square over 2R. So the power dropped to half of the value, so that's why they call it half power frequency. And those half power frequency can be obtained by setting Z equal to root 2 times R. Okay, because again the current will be equal to V over R divided by root 2. W1 can be obtained from this one, W2, and of course that will be the resonance frequency. Okay. W2 minus W1, we said that we call it a bandwidth, call it B, bandwidth. And also bandwidth can be obtained by dividing the resistance of the circuit divided by the inductance. So R over L will be equal to the bandwidth. Okay, so again R over L will be equal to the bandwidth, and also we know that also Q, which is the quality factor. So quality factor for the series resonance will be equal to XL over R. Okay, and XL of course will be equal to omega L over R. Okay, so again we can replace replace R with this, or we can replace R over L with W0 over the quality factor. Okay, or also the quality factor can be replaced by also W0 CR, right? Because the quality factor is XL over R, or XC over R, and XC is equal to 1 over omega C. Okay, so the quality factor omega naught can be also obtained from omega naught over B, right? Now if the bandwidth is narrow, that means B is small, then the quality factor will be high. Okay, so as the bandwidth go down, quality factor goes up, so there will be more selectivity. Again, this is the definition of the quality factor, XL over R or XC over R, and they call it and it is it gives the ratio between the peak energy stored in the circuit over the energy dissipated by the circuit in one period at resonance. So energy stored over the energy dissipated at resonance. Okay, that is the quality factor. Okay, and if the quality factor is large, it's more than 10, then we can do approximation in which W1 will be equal to W0 minus B over 2, or W2 will equal to also W0 plus B over 2. Let's look at this simple example. Let's say that in this circuit we have R, we have L, we have C, and he said find the resonance frequency and half power frequency. So we need to find W0. So we know that W0 is equal to W0 1 over root L times C. If we like to find W0, so L and C are given. If we like to find F0, of course we need to divide over here by 2 pi. So that will give us the resonance frequency. We need to find half power frequency, so we need to find W1 and W2. So again we know from the formula how to obtain W1 and W2, since the value of the quality factor is more than 10. Because the quality factor can be obtained from again either XL over R or omega naught over the bandwidth, and the bandwidth can be obtained from here. So that will give us the value of W1 and W2. He said also calculate the quality factor. Okay, we have already did that one. Determine the amplitude of the current at W0. Of course, at W0 at the resonance frequency, the current only will be limited by R. So it will be 20 peak with angle 0 divided by R, which is 2. So that will be the value of the current, the peak. If you like to find the root mean square, of course, we need to divide that one by root 2. The current at half power frequency, so I guess we need to divide the value by root 2. Okay, so that will give us the the current at the half power point. Okay, for the parallel resonance, this is the parallel resonance circuit. So the elements are connected in parallel, and it will occur when the imaginary part of y is 0, because those are connected in parallel. So y will be equal to 1 over r plus 1 over j omega l plus 1 over j omega c. So that will be y. So when the imaginary part is 0, the resonance will occur, and again we'll find that the resonance frequency will be equal to 1 over root L times C. So that will be for the resonance frequency, and for the quality factor it will be equal to the other way around. It will be R over XL, or R over X C. Okay, so now again, if we plot the relationship between the voltage and between the frequency, we'll find that at resonance, the voltage will be maximum. Okay, since the current will flow only through the resistor. Okay, so those two will be just will have 0y, or Z will be an open circuit for those two. So the current only will flow through the resistance. So as a result, the value of the voltage will be large. So that will be the peak. So if we divide that one by root 2, then again we call it the half power frequency, W1 and W2. And again we have the bandwidth. Okay, so this is the W1, this is W2 in general. Bandwidth will be the difference between the two, or they will be also equal to 1 over RC. Okay, quality factor will be equal to R over XL, or R over XC. And also it can be obtained from omega naught, which is the resonance frequency divided by the bandwidth. Okay, so these are the summary for the differences between the series circuit and for the parallel resonance circuit. So for the resonance frequency, we have exactly the same formula. For the bandwidth, same formula. For W1 and W2, we have the same formula. Also if the quality factor is more than 10, we have also the same formula. The only difference will be in the quality factor. Okay, so in the series resonance, we have R. We have XL over R, or XC over R. In the parallel one, we have the other way around, but the rest will be identical. Okay, in this parallel circuit, R, L, and C are given. He said calculate the resonance frequency. So omega naught can be calculated from omega naught will be equal to 1 over root LC. So we need to find or L is given, C is given, and also we can calculate the quality factor from, because this is resonance, from R over XL. Okay, or you can also utilize the bandwidth as well. Okay, so omega naught is that one, Q will be that one. Okay, and then you can find the bandwidth from Q. You can find W1 and W2 since the value of Q is more than 10. Okay, and if you like to find again the current, so at resonance the current will flow only through the resistance, so it will be equal to 1.2. Now you can calculate the power. You can calculate so that will be the maximum power, and then the half power frequency. Okay. If we look at the practical resonance circuit, so this circuit, they call it a tank circuit. So actually with the inductor, the inductor of course is made from winding. Then that winding of course will have some resistance, so the resistance cannot be neglected. So in this case the total Y will be equal to those two are connected in series, so it will be J omega C plus 1 over R J omega L. Okay, if you multiply by the conjugate, and then if you take the if you cancel the imaginary part, since Y will have only real part, so the imaginary part will be equal to 0. Then you can find the resonance frequency for this circuit, in which R is included as part of the inductance. Okay, so you'll find that actually the resonance frequency with the inclusion of R will be almost the same as the resonance frequency without R. Okay. Let us look at this example over here. He said determine the resonance frequency of the circuit. So over here we are giving capacitor bank, we are giving inductance, we are giving also a resistance which is part of the inductance. So if we write, or we like to find the total Y, so this one will be the total Y. Those two are connected in parallel, so it will be J omega of this one plus those two connected in series, so 1 over 0.1 plus J omega 2. Okay, so now if you multiply by the conjugate, and then of course at resonance the imaginary part will be equal to 0, so then you can find omega naught. Okay, system response characteristics. Okay, so now in summary, we know that for the series resonance, the impedance will be minimum at the resonance. For the parallel resonance, the impedance will be maximum at resonance. We have parallel circuit. Okay, so now let us look at the at system response characteristics. So we are saying that in power system, the response of the system is equally as important as the source of the harmonic. Okay. In fact, power systems are quite tolerant of the current injected by harmonic, unless there is some adverse interaction with the impedance of the system. Identifying the source is only half the job of the harmonic analysis. Identifying the source of the harmonic, of course. The response of power system for each harmonic determine the true impact of the non-linear load on the harmonic voltage distortion. There are three primary variables affecting the system response, and those variables are system impedance, presence of capacitor bank, and the amount of resistive load inside the system. At fundamental frequency, power systems are primarily inductive, and the equivalent impedance is sometimes called short circuit reactance. Capacitive effects are frequently neglected on utility distribution system and also in industrial power system. One of the most frequently used quantity in the analysis of the harmonic power system is the short circuit impedance, to the point on a network at which a capacitor is located. If not directly available, it can be computed from the short circuit study result that give either the short circuit megavolt ampere or the short circuit current. Okay, so then we can calculate the system impedance from the short circuit calculation. So those will be given. Short circuit at a certain bus will be given, and we know the voltage of that bus. So the voltage square divided by the short circuit megavolt ampere, that will give you the source impedance, what we call the short circuit impedance. System impedance. So the source impedance or the system impedance is a complex quantity consisting of both resistance and reactance. For industrial power system and most utility system, the impedance is assumed to be purely reactive. So the system impedance can be assumed to be purely reactive. The inductive reactance portion of the impedance changed with the frequency, of course, because XL is equal to 2 pi FL, so it is changing with the frequency. The reactance of the H harmonic is determined from the fundamental impedance reactance. Okay, so once we find or if X1 is given, which is at fundamental frequency, then we can find the reactance at any harmonic. In most power systems, the resistance does not change significantly when studying the effective harmonic, less than 9. So the resistance of the system will stay almost the same. The change will be in the reactance since it depends on the frequency or on the harmonic order. For line and cable, the resistance varies approximately by square root of the frequency. So this is the variation of the line and cable. So their system resistance depends on the frequency. For large transformer, the resistance may vary almost proportional with the frequency. So for large transformer, also the resistance will be vary with the harmonic order. But for the overhead line and cable, the resistance of the system will vary with the square root of the harmonic order. Okay. At utilization voltage such as industrial power system, the equivalent system reactance is often dominated by surface transformer impedance. A good approximation of the X short circuit or X source impedance may be based on the impedance of the surface transformer only. Okay. Transformer impedance can be, of course, determined from the size of the transformer and from the kilovolt. Okay, so then kilovolt square divided by the size of the transformer, that will be the base impedance multiplied by the per unit, that will give you the impedance in ohm. So those are the unit transformer. Let's assume that the impedance is predominantly in a reactive. For example, for 1500 kilovolt 6% transformer, the equivalent impedance on 480 size will be equal to the kilovolt divided by square divided by the size times x per unit. So that will be 9 per unit. Sorry, in ohm, 0.0009 ohm. Shunt capacitor either at the customer location for power factor correction or on the distribution system for voltage control dramatically alter the system impedance. So the capacitor bank will change the system impedance variation with the frequency. Capacitor will not create harmonic but serve harmonic distortion, can sometimes be attributed to the present, but severe so they will not create harmonic, but severe harmonic distortion can sometimes be attributed to their present, because they are present then in the system that will create a lot of harmonic distortion. While the reactance of the inductive component increases with the frequency, the capacitive reactance of course decreases, as it is shown over here. Both capacitors are rated in terms of kilovar or megavar at given voltage. The equivalent line to neutral capacitive reactance at 100 frequency can be obtained, or the value of the capacitor bank can be determined from the size of the capacitor bank in megavar or in kilovar and the rated voltage of the system where the capacitor bank are connected. Okay, so again we have series resonance, we have parallel resonance. Series resonance can occur in a series circuit that having equal inductive and capacitive reactance. The resulting impedance is the lowest value. So as a result, the current will be highest value. Parallel resonance occur in parallel RLC circuit having equal inductive and capacitive. The resulting admittance is the lowest value, and even a small exciting current can produce significant high voltage. طبعا the admittance is the lowest, but if you look at the impedance, it will be the highest. Okay, so to find the resonance frequency, we know that 1 over LC. Okay, at resonance also the voltage and the frequency will be dominated. The true impact of non-linear load on the harmonic voltage distortion can be determined from the response of the power system at each harmonic. So we have to look at each harmonic. Okay, for example, over here, let us see this figure. So over here we have a source of the harmonic, we have capacitor bank, then we have the impedance of the transformer, and this is the impedance of the transformer, and that is the source impedance. This is also another impedance. So over here we have a capacitor bank in parallel with those system impedance. So parallel combination power system inductance and power factor correction capacitor at a non-linear load. the voltage of the capacitor bank will be magnified and heavily distorted. Okay, so this is the system with the parallel resonance problem. Okay, so they are feeding capacitor bank. At the resonance frequency, the apparent impedance of the parallel combination of the equivalent inductance and capacitance as seen from the harmonic current source become very large. That means course MZB will be those are connected in parallel, the capacitor, and then we have the inductor, and resistance will be part of that inductor. Okay. So that will be the resultant Z, and then we can find XR, and XR will be XL over XL times XC. Okay. Quality factor of a resonance circuit that determine the sharpness of the frequency response. So Q will determine whether the response is sharp or not sharp. It is clear that during parallel resonance, a small harmonic current can cause large voltage drop across the apparent impedance. Okay. The voltage of the capacitor bank, of course, will be magnified. Current flow in the capacitor bank and through the transformer will be magnified Q time. This phenomena will likely cause the capacitor bank to fail, fuse blowing, transformer overheating. Okay, and again this is the parallel resonance. We'll have to find X, and then if you have to find the quality factor, we'll find what will be the impedance of the system. Okay. Power system analysis typically do not have RL. L and C readily available, and prefer to use other form of relation. They commonly compute the resonance harmonic based on the fundamental frequency and rating using the following equation. So we can find H. If we don't find it, then we can utilize the size of XC and the size of the transformer to calculate the harmonic order. Okay, let us look at this one, this example over here. See that industrial load bus where the transformer impedance is dominant, the resonance frequency for 1500 kilovolt ampere 6 per unit transformer and 500 kilovar will be given by, so from the size of the transformer and from the size of the capacitor bank, we can determine what will be the harmonic order, and it comes as 7. This figure shows the effect of the capacitor bank size on the impedance seen by the harmonic source. Okay, so at the size of the capacitor bank go down, the peak of the impedance goes up. Okay. Let us look at this example. We have over here we have to investigate the resonance in a parallel RL with XC equal to 60, XL equal to 0.495. Assume a Q equal to 3, and we need, of course, to find the resonance frequency, so it will be XL over XC. The quality factor is given, so from there you can determine R. Okay, and of course we're going to find XR, which is H times XL, or square root of XC times XL, and this is the the total impedance at resonance. So the total impedance at resonance will be only R, which is equal to 16.35. In example 5, he said calculate the harmonic order for the this system. Okay, so what we have transformer that will step down the voltage from 15 to 0.4, and the size of the transformer is 2. The impedance 6.5%. Okay, for the capacitor, we know the size of the capacitor bank, and we know the voltage. Of course, to find the harmonic order, that means we need to find H, we need to find XR. Okay, so to find H, of course, we know that H is equal to the square root of XC. X is square root of XC over XL. Okay, and we know that XR is HXL or XC over H, or square root of XC times XL. And then of course we're gonna find R. This is a series resonance, so we know that the quality factor Q, okay, the quality factor Q is equal to XL over R. Okay, so from here we can find directly the value of XC, because the size is given, the voltage is given, so we know that XC will be equals to voltage V line square over Q, so V square 0.4, this one will be 0.4 square 0.4 kilovolt, K square over Q. Q is in kilovolt ampere, we need to convert it to mega, so it will be 0.25 divided by 0.25, so that will give us the value of XC. Okay, for XL, of course, we have the transformer. We have the transformer impedance, which is given as 6.5%. We need to find it in ohms, so we need to find Z base on the low voltage side. So Z base will be equal to V square divided by S base. Okay, so V square will be 0.4 square divided by S base 2, so that will give us Z base, and then we can find X for the transformer. So we can find transformer reactance, which will be the per unit time the base value. But in this case we don't have only the transformer impedance, but we have also the source impedance. So to find the source impedance, we are given the short circuit level over here, and we are given the voltage, but of course we need to refer that one to the low voltage side. So from here, we do it maybe over here. So over here I will call this one XS. So XS. Of course, if you like it, if you like to find it, if you like to find it on the high voltage side, I mean, that's fine to say V square over S, and then you refer it to the low voltage side. So you can do that one. So let us do it in that way. So this one will be 15 square, okay, divided by 20, and then we need to refer to the low voltage side, so we're going to multiply it by the low voltage side, which is 0.4 square, divided by the high voltage side, 15 square. So that will cancel that, so effectively it will be 0.4 square over 20. So that will give you the system impedance, and then we need that XL, this XL will be made from two components, will be made from XT and from X source. Okay, the solution is given for you over here. So this is the system impedance, 0.4 over 20, the transformer, so the base time per unit, X for the reactive, for the capacitor bank, and then you can find the harmonic order, and that will be 7. Okay, in part B he said investigate the effect of capacitor bank and the short circuit capacity. So we need to see what will be the effect of changing the size of the capacitor bank and also the short circuit level. So this one and that one. Okay, so we have to do a several scenario, or actually we need them in just to repeat the procedure again, but with those new values. So the initial value for the short circuit level, it was 20, and now it will be 10. The initial value for this one, it was 250, now it is 200. So just we need to repeat the procedure again. Of course I did it over here by using the per unit. So you can do it either by the per unit or directly by an ohm, like what we did initially. Okay, so this one will be the result. So you will notice that the harmonic order is increasing actually with the increase. So if we look at the harmonic order, for the same short circuit level, increasing the Q, or the size of the capacitor, will increase the harmonic order up to a certain level, and then again the harmonic order will start to decrease. Okay, actually we are looking over here, sorry, we are looking over here because this is only one case, right? So we are looking at this case, short circuit level 20, and we are increasing the size of the capacitor bank. So as we increase the size of the capacitor bank, we're gonna reduce the harmonic order. Okay, so if the size is 100 kilovar, harmonic level will be 11. Increasing it to 500 kilovar at same short circuit level will reduce the harmonic order to around 5. And this is the summary. So let's say that the resonance or the frequency decreases as more critical as the capacitance of the bank increases, so the size of the capacitor bank increases. Let us look at example number 6. And over here, what we have also a source impedance, we have transformer, we have capacitor bank, and over here we connect a load. And say that 380 over 36 kilovolt transformer with the size of 100 megavolt ampere with X 12% supply a load of 50 megavolt ampere at 0.8 power factor. So from here we can find P is time cosine, so that will give us P. A capacitor is to be installed to improve the power factor to 0.95. So the initial power factor is 0.9, and now we like to improve this power factor to 0.95 by placing capacitor bank. Okay, so then we need to calculate what will be the size of this, or what will be the value of XC. So what will be the value of XC such that the power factor will increase to 0.95. Well, this one, so guess what we like, what we did it, we did actually a similar one previously. So this is our system, this is P, this one I will call it Q1 of the system, and of course Q1 can be calculated from here, so it will be S sine, that will give us Q1. And now we like to improve the size, we like to improve the power factor to 0.95. So then what will happen, what we're gonna do, we're gonna put a capacitor bank. So then from there to there will be QC. So this is our initial Q1. From there to there, this is Q1, and over here we have Q2 or Q total. Okay, theta 1, this is theta 1, can be obtained cosine inverse. Theta 2 also can be obtained from the cosine inverse. So we know that QC, we like to find QC will be equal to P tan theta 1 minus tan theta 2. So P is given, theta 1, theta 2 is given, so that will give us QC, and then we can calculate the value of the XC from V square, which is 36 divided by QC, by that value, and that will give us the value of XC. Of course, for the transformer we can find XT for the transformer. So we are given the we are given the following. We are given the size of the transformer, we are given the voltage, and over here also we can calculate XS, because we are given the short circuit level and the voltage level is given. So we can do the calculation just like what we did previously. Okay, so this is the way how to find XS, the short circuit or the source impedance from the short circuit level, and this is how to find the transformer reactance. Okay, so again we know the per unit, we multiply it by the base, and that gives us the reactance of the transformer. And this is how to find the capacitance. So we know that the size of the capacitor bank will be, or Q will be B tan theta 1 minus B tan theta 2, and that will be 7. Then we can calculate XC, we can calculate C, and now we can find the harmonic order again from XC divided by the transformer reactance and the source impedance, so it will be the 9th harmonic. Okay, so we can do it directly, or we can utilize the per unit like what I did over here. So I choose a space of 100, then I did the calculation by using the per unit. Of course we're gonna have the same result. Series resonance, there are certain instances when a shunt capacitor and inductance of the transformer may appear as a series LC, like this one over here. So over here what we have capacitor bank in series with the with the transformer, so that will make a series resonance for the harmonics. Okay, so now if the resonance frequency F1 corresponds to a characteristics harmonic of the nonlinear load, the LC circuit will attract a large portion of harmonic current that is generated in distribution system. Okay, so that means over here what we like over here when we design this system, this is capacitor bank and with the transformer, but if we choose a proper value of both L and C, so that can short circuit all the harmonics, so the harmonic will not affect the load that will be connected after this place over here. Okay, so this one again, that one we call the series resonance, or this one also we can call it a series resonance. The transformer reactance with the capacitor bank that are connected in series. Okay, the highest voltage distortion is at a remote point or on an adjacent feeder served by the same substation transformer. Of course, if we have a series resonance, if a series resonance happens in the system, of course that will cause high voltage distortion. So that's why we need to make sure that the will not go into series resonance. So when we design our system, so we have to make sure that the filter that we are designing will not make resonance, because resonance will cause a high voltage distortion. So what will happen during resonance? During resonance, the power factor correction capacitor form a series circuit with a transformer, and because they have a harmonic source that flow from them, so the harmonic source represents the harmonic by nonlinear load. The series combination of transformer inductance and the capacitance will be very small and only limited by the resistance. Of course, during resonance, XL will cancel XC, so as a result, the current will be limited only by the resistance. Okay, and the voltage at the capacitor bank will be magnified and it will be highly distorted. Of course, again, this is during resonance. Okay, so the voltage across the capacitor bank will be equal to the total voltage during the harmonic, and since again the capacitor bank will be connected in series with the transformer in this case, okay, so this one between there and there we have the harmonic the harmonic voltage. So then to find the voltage across the capacitor bank, we can use a voltage divider. So it will be the total voltage times the reactance of the capacitor divided by the summation, and that will be this value at resonance. So you will notice that really the value of the voltage harmonic across the capacitor during resonance will be very high. Okay, in this circuit you will notice that we have both. So this is our series resonance, and then we have also another reactance that represents the reactance of the source. Then this part and that part will be connected in parallel, so as a result we're going to have parallel resonance. So we have series and we have parallel. So in many systems with potential series resonance problem, parallel resonance also arises due to the circuit topology, such as this one. One of these is shown below, where the parallel resonance will be formed by the parallel combination of X source and the series combination of the transformer and the capacitor bank. Okay, the resulting parallel resonance frequency will be smaller than the series resonance frequency, right? Because we know that at resonance, we know that to find the resonance frequency, it is equal to 1 to y L C. So that will depend on the value of L and C. So the value of L for this case will be only transformer, but the value of L in when we have parallel resonance, it will be both. It will be XT and also will be X source. So that will increase the value of L. As a result, it will reduce the value of the frequency. So that's why we are saying that the parallel resonance frequency will be smaller than the series resonance frequency. Okay, and this is the harmonic order for the parallel resonance. So we have XC, and then those two will be connected, and we can draw the frequency response for the circuit as shown over here. So over there, that will be the series resonance. Okay, and we know that Z for the series resonance will be very small, and it will be limited by R if we have R, whereas Z total for the parallel resonance will be very huge. So over here we have parallel resonance, over here we have a series resonance, and series resonance harmonic order will be determined by XC and XT, and the harmonic order for the parallel resonance will be determined by XC and both XT and X source. Okay, so over here, if we look at this frequency response, which is again the impedance against the frequency, we can see that we have two peaks over here. So that will indicate we have parallel resonance over here, and we have over here series resonance, and maybe again over here we have another series resonance. Same thing over there. So any peak that indicates the parallel resonance, any value that indicates the series resonance. What is the effect of the resistance, of the system resistance, and also of the load resistance on the parallel resonance? Well, the resistance will damp the system. It will damp the response, and then and because it damp the response, then it will prevent catastrophic voltage and current. So because we have small resistance, that can really damp the system resonance. Variation of the parallel resonance circuit impedance characteristic for various amount of resistive load in parallel with the capacitance is shown over here. So to say that, you see that if we have no resistance, then our response will be peak. So look at the Z response if zero resistance is there, but adding only 10% resistive load can really reduce significantly the impact of this peak impedance. Likewise, if there is a significant length of line, of overhead line or cable between the capacitor bank and the nearest transformer, also that will reduce the resonance. It can suppress the resonance, since the line and the cable will add resistance to the equivalent circuit. Load and line resistance are the reason why catastrophic harmonic problem from capacitor and transformer are seldom seen. So because of the existence of the resistance, so that's why we don't see big problem in the distribution system. The most trouble resonance condition occur when capacitors are installed on substation, because it will be now very close to the transformer. We don't have overhead line or cable that will add a resistance. And same thing if the capacitor bank is also added at the industrial facility, because it will be also very close, so that can really cause a resonance problem. So we have to be very careful when we are designing our system. So in this case, where the transformer dominates the system impedance and has high X over R, then the relative resistance will be low and the corresponding parallel resonance impedance peak will be sharp. As a result, that may cause the capacitor, the transformer, and the load equipment to fail. While utility distribution engineers may be able to place feeder bank with little concern about the resonance, okay, so if they place the capacitor away from the transformer, at that time you should have no major issue with regard to resonance. And studies should always be performed for industrial capacitor application and for utility distribution, for utility substation application. Again, if you place the capacitor bank near the transformer, that may cause problems. So you need to do a full study about that case in order to investigate what will happen to your system. In fact, selecting capacitor size from manufacturer table to correct the power factor based on the average monthly billing data tend to result in a combination that tune the system near the fifth harmonic. This is one of the worst harmonic to which to be tuned, because it is frequently the largest component of the system. Okay, so as a result, resistive load will damp resonance, of course, but it will not, of course, the harmonic will be independent from the resistive load. But over here we are talking about resonance.